Hello, everyone. So in this lecture and the next lecture, I'll be talking about end-to-end autonomous driving, which is currently the trend for next generation self-driving systems. So just to give a quick recap on traditional autonomous driving stacks, I think Moshkan also mentioned from last lecture. So given some sensor input, a traditional autonomous driving stack will first do a perception task, something like object detection or semantic segmentation. And when we identify all the objects, there's another tracking component using traditionally Kalman filters. And then based on the past tracks and past trajectories of each agent in the scene, we can do a prediction for future trajectories. And based on all that information, a planning component will be responsible for directly directing where the ego vehicle is going to go. And then the controller, like a predictive controller or PID controller, will be responsible for carrying out the planned trajectories. So there are a few problems with this design. This is very modular, and you can basically divide up your team into different components and try to optimize each component separately. But when you want to put all the individual components together, it's very challenging from an engineering perspective. There are a lot of complexities involved in merging all the components together. And because at each step we're doing some kind of abstraction and a specific task, there are a lot of information that's being lost along the way. For example, from perception to tracking, perception is going to, for example, produce some bounding boxes, and that doesn't really include any appearance data from the sensor input. So the tracking would not be able to benefit from those information. And similarly, from tracking to prediction, we don't really have context information, we don't have uncertainty, and we don't know the intention of each agent. And from prediction to planning, we don't know context, we don't know uncertainty, and the prediction also cannot really model the multimodal behaviors of agents, because typically they select top K future trajectories to get to the planner instead of a full distribution. And specifically because of the lack of context and uncertainty, certain errors from the upstream, for example, perception, I made a mistake, I misidentified some objects, those errors can propagate through the entire process because there's no information for the downstream task to correct the upstream mistakes. And finally, because we're optimizing each component independently, there's a objective misalignment problem here. So what do I mean by that? For example, let's focus on perception and say I have a object detector. Right now, I want to optimize the object detector's performance. So in this example, the object detector is missing some objects that's marked in red. Those objects are either parked on the side of the road or far away to the back of the vehicle. So those objects, even though I'm penalized for not detecting those objects in my perception task, those objects do not necessarily impact the final driving performance. But on the other hand, some objects could be misidentified and they are very crucial to the driving task. So the standard metric that we use to evaluate each component independently may not align with the final objective of self-driving, which is to drive the car safely. So this leads us to the end-to-end system, which simplifies the entire process by replacing all the independent individual components with a neural network or a series of complexly designed neural network that can be trained end-to-end. So basically, you want to go from the sensory input directly into actions. This can be implicit actions like steering angle or acceleration, deceleration, so on. Or it can be explicit. For example, I want to output the planned trajectory. So I want to quote a tweet from Tesla, where in 2023, they replaced their system, FSD system, with a single end-to-end neural network. And they claim that they replaced over 300,000 lines of C++ code, which kind of highlights how much this kind of end-to-end system can simplify the engineering challenges involved with traditional driving stacks. So in these two lectures, I'm going to talk about, first of all, the early end-to-end methods, and which kind of lacks interpretability. So a lot of the later works use many different techniques to improve the interpretability of the end-to-end self-driving systems. And in this lecture, I will go through some of those. And in the next lecture, I will be focusing on the learning strategies for those end-to-end architectures, as well as the evaluation methods for evaluating those architectures, which includes open loop and closed loop simulation. So even though I mentioned that, Tesla, which is a very, even though I previously mentioned Tesla just recently switched to end-to-end system, but end-to-end actually started really early in the development of autonomous driving, all the way back to the 1980s. So in 1980s, CMU developed the Alvin, which is an autonomous driving testbed, and they equipped the vehicle with a fully connected neural network with a single hidden layer. And they input a video camera and a rangefinder, a laser rangefinder. And the output of the network is going to be steering control. So this is way ahead of its time. And if we want to go forward in time and see what's the next work in end-to-end method, we need to go forward almost 20 years. And Yang LeCun at that time built a off-road robot, and he wanted to perform obstacle avoidance task. So he equipped the robot with a stereoscopic camera setup and using a single convolutional neural network, which is state of the art at that time, to directly predict the steering angle to avoid obstacles in off-road conditions. So what really bootstrapped the recent development of end-to-end self-driving is the NVIDIA's Dave 2 system, where they, similar to the Yang LeCun, they also use a very simple convolutional neural networks, which takes input images and then directly output vehicle controls. But what's really nice about this is that they demonstrated that using this simple system, you're able to actually drive on the road in real time at pretty decently high speed. And this is also thanks to the advance in GPU, where they use GPU accelerated computing to accelerate the computation for those convolutional neural networks, which we kind of take for granted these days. And you can also see how simple the entire architecture is. And I believe some of you can easily code this in like less than 1 hour. So some later work also introduced improvements to the simple CNN-based end-to-end model. One of them is to be able to incorporate temporal data, because all the previous work, including the NVIDIA's self-driving work, they take single frame as input. So, but in reality, when we drive the car on the road, the sensors are continuously collecting data. So we want to be able to take advantage of the data that we collect in the past. And to do that, this work from 2017 proposed to use short-term memory to connect or to serve as some kind of memory to the system. So for those uninitiated, the long short-term memory component looks something like this, which looks quite complicated, but I'll break it down and you'll realize it's quite intuitive. So there are two hidden states. One of them is called the cell state, which represents the long-term memory. And there are two operations being done on it. The first one is the multiplication and the other one is the addition. So the first one, multiplication, is multiplied by a sigmoid gate. So this kind of sigmoid is between 0 and 1. So this kind of represents a forgetting operation, removing unnecessary information from the long-term memory. And the addition operation naturally represents adding new information to the long-term memory. But obviously, we don't want to add all the information from the current frame or from short-term memory directly to the long-term memory. So we also have a sigmoid plus a multiplication to filter out some unnecessary information from the current state and then add the filtered information to the long-term memory. So this completes the update of the long-term memory. And then we can then add another filter to the long-term memory to extract information that's relevant to our short-term decision-making to arrive at a new short-term memory. So this is the process of long short-term memory. And this serves as a very nice architecture to process sequential data, including videos for end-to-end self-driving. So another important advancements or improvements to the traditional self-driving stack is called conditional imitation learning. So we want to go beyond lane following and obstacle avoidance, like all the previous work we're trying to do. So what I mean by that, so let's say we have a situation where our ego vehicle is approaching a intersection. And in the previous work, when the model is trained on lane following or obstacle avoidance, you have many different options. As long as you stay on the road, that's fine. But in this case, because we're at the intersection, we want to be able to control the vehicle where to go, right? So you may say, okay, that's easy. So in addition to the camera image, we'll just add another input. Let's say a command that represents if I want to go left, right, or straight to the input and concatenate everything together, and then feed that to the neural network and to produce some action. So this setup makes the action conditioned on some commands, hence the name conditional imitation learning. And imitation learning basically means you're trying to imitate what the human driver is doing. And this is a technique that I'll introduce in more detail next lecture. But this kind of approach has a major flaw of naively concatenating everything together because in the subsequent neural network, let's say it's a fully connected network, so it's a linear layer. After training, you could have a weight that looks something like this, where it will completely ignore your command. And you will have no control over this because everything is trained end to end and it's a black box neural network. So can't do anything about it. So in this paper, instead, what they're proposing is to have a switch mechanism where you have multiple small neural networks that is responsible for outputting action for each command. So if you have 3 commands, you would have 3 small neural networks. And if you have more commands, you have more. And if you're familiar with large language models, this is similar to a mixture of expert, where each small module is only going to be activated some of the time when it's necessary. And this makes sure that the command will not be ignored by the subsequent neural network. And this kind of architecture, you're going to see this in a lot of the later end-to-end work that's going to need some conditioning on command or text input. So in summary, those early end-to-end methods, they provide a holistic and data-driven optimization for self-driving architectures, which is better because you're directly optimizing your goal, which is to drive safely and not crashing. They don't require as much engineering complexity. As you saw, the neural networks are often pretty simple with convolution and fully connected layers. But the main problem with those early architectures is that they really lack interpretability, meaning that if something goes wrong, you don't really have a easy way to analyze and to understand which part of the network went wrong and how to fix that. because everything is trained end-to-end and everything is a single fused neural network. It's very hard to understand what's going on. So there are a lot of later work that tries to improve the interpretability of end-to-end self-driving systems. There are different ways to do that. The first one I want to talk about is based on general machine learning techniques and specifically uncertainty. So uncertainty kind of represents what the model is confident about. And knowing, if we know that, then we have some idea of what the model is trying to do and what the model thinks. So before I get into uncertainty and uncertainty estimation, it's important to make the distinction between deterministic and probabilistic machine learning models. So in a normal machine learning model, let's say a classification task, here I have a picture of a capybara, and I have a neural network that's trained to classify the image. And typically the model is trained using gradient backpropagation. And as a result, the output is going to be deterministic. Well, you may say, okay, I see some kind of confidence value here clearly, and this looks like a distribution because they add up to 1. And by construction, yes, they do, because typically you apply softmax to that. But that's actually kind of deceptive, because if you run this model multiple times on the exact same input, you will get exactly the same result. So that really it's deterministic. But you can still do some uncertainty estimation by proxy. For example, you can simply treat the confidence value output by this model as the confidence or certainty of the model, or you can estimate, or you can compute the entropy over all classes and treat that as the uncertainty estimation. But another way to do machine learning is actually a probabilistic one. So in this case, we can update the model's parameter. We can treat the model's parameter as a distribution instead of a deterministic value. And we can update the parameters using Bayesian frameworks based on this formula. So you can update the parameters given the data during the training. And because of that, the output of the model is going to be distributional by nature. Let's say for regression tasks, for example, if you model your output as a Gaussian distribution, it will be parameterized by mean and variance. So in that case, you can actually estimate the true uncertainty of the output. So what do I mean by true uncertainty? Well, there are two types of uncertainty in machine learning. One of them is called aleatoric. So this is the uncertainty inherent to the task that you're doing. So for example, here I have a picture, and in the very, very far away, there is a pedestrian, but that pedestrian is represented by very few pixels. So you're uncertain about, or the model may be uncertain about that prediction, not because the model cannot recognize the pedestrian, but it's because the pedestrian is far away and maybe it's occluded. It's not represented by a lot of pixels. So it's the lack of pixels and occlusion that's causing the model to be uncertain. And that uncertainty is not really reducible because there's not information for you to determine that's a pedestrian. On the other hand, there's another type of uncertainty called epistemic uncertainty. In categorical distribution classification tasks, it's typically estimated by mutual information. So this actually represents the uncertainty due to the lack of data. So in this example, you see something on the road, well, but you don't know what it is, or the model would not be able to know what it is, but not because the model cannot see it clearly, but it's because the model probably hasn't seen anything like this before. So it's due to the lack of data. And you can probably tell that these two types of uncertainties are very useful in practice to quantify. Aleatoric uncertainty will tell you, for example, well, if something is uncertain, but epistemic uncertainty will tell you something is novel and maybe you should do something about it, collect it into your data and update the network to make it not more robust to edge cases. So if that's the case, why don't we just train all the networks to be Bayesian, according to the Bayesian principle, and estimate true uncertainty in self-driving? The big problem is during the Bayesian update, we need to know the data distribution according to the Bayesian framework, but this is impossible and intractable in practice. But luckily, there are ways to approximate this Bayesian update and approximate the posterior distribution of the parameters. There are several ways to do that. The first of all, we can use an ensemble of models, which basically means we train multiple models randomly initialized on the same data. And then at the end, they will have similar performance, but they will be slightly different. So to understand why this kind of works for uncertainty estimation, especially for epistemic uncertainty, you can take a look at a example of a curve fitting problem. Let's suppose we are trying to fit a curve to those data points. So for the regions that we have those data points, the data points are dense. If we fit multiple models, you'll see that the performance or the curve will look pretty similar because we have the data points there. But outside of the region where we have the data point, the curve is going to kind of diverge because with random initialization, you're going to get vastly different curves. So that's kind of an intuitive understanding of how that works. But for more theoretical analysis, you can check out Yarengal's PhD thesis on the uncertainty in deep learning. So this type of uncertainty is actually applied to end-to-end driving in 2020, also by Yarengal's group, I believe. So they train an ensemble of end-to-end self-driving system, and then based on the prediction from each system, they aggregate the predictions from each model in the ensemble and perform planning under uncertainty. So another way to do uncertainty estimation is called Monte Carlo dropout. It's pretty similar to ensemble, but instead of training multiple models, in this case, you only train a single model. But the requirement is that your model will need to have some dropout layers. So recall that in standard neural network training, you can apply dropouts, basically meaning disabling some neurons during the training process. And the disabling of neurons is stochastic, so it's completely random for each forward pass iteration. And this will make your model more robust and less likely to overfit. But it turns out during test time, you can actually keep enabling the dropout layers by every forward pass, you randomly disabling some neurons. And that's kind of like an ensemble where you need to have multiple output, and in the end, you will have a distribution of output. And Yarengal and Zobin show that this is a valid approximation to the Bayesian neural network. So later on, they applied this Monte Carlo dropout problem or technique to end-to-end self-driving, where they try to quantify the different uncertainty type in trajectory planning in end-to-end self-driving. And what they found is if you consider the epistemic uncertainty, which in classification tasks is mutual information, this is actually a very good indication of when the vehicle is going to make a mistake. So in those cases, you can either have another system to correct it, or you can collect that kind of data and retrain the network to make it more robust. But in any case, this is a good indication of those problems in the neural network. So the second type of machine learning based technique I want to talk about is saliency and attention, or attention maps. So whenever you see something like this before, it's likely a saliency or attention map from a neural network. This lets us understand and pick into the inside of neural networks and understand what the neural network is paying attention to. So on a from the simplest form of saliency map is simply the gradient of the output of the neural network with respect to the input. So this kind of represents how much the input for an image, how much each pixel contributes to the final output decision. And there are a lot of variations of this gradients and back propagation based methods. If you want to check out more, there are a couple of popular ones here. So all the way back to, if you remember that NVIDIA car, that group also did an analysis of a saliency map for their vehicle, and they kind of showed that saliency kind of will demonstrate what the model is paying attention to, in this case, the vehicle, the objects, and the lane markings. They also did a counterfactual intervention by moving one of the lane marker slightly to the right and observe a change in the model's prediction of steering angles, which indicate indeed that is what's affecting the model's steering output. And later on, saliency map has been used to train another model, which tried to predict when the model is going to make a steering mistake, similar to how Darren Gell's group found that epistemic uncertainty can be a good indicator of steering mistakes. But in the end, both methods doesn't really architecturally improve the interpretability of an end-to-end system. They're kind of retrospective in some sense. So to make the model more interpretable by design, some group proposed to, instead of learning to directly output the action at the control, the steering angle, and so on, we can divide this problem into first predicting some affordance values, and then based on the affordance values, we design a interpretable controller that's handcrafted to drive the vehicle. So what do I mean by affordance, and what are some examples? Well, for lane keeping and lane changing, the affordance can be the relative angle to the road center, the distance between the ego vehicle to different markings on the road, or the distance between the ego vehicle to other vehicles on the road. So basically, you want to go directly from the sensor input to outputting those affordance values. And for more complex urban driving situations, you also want to be able to predict, for example, stop signs, red traffic lights, and speed signs, and so on. Now, the problem is this kind of system, they provide very good interpretability because you know exactly what the model is predicting and why it's doing certain actions based on the affordance. But for very complex driving conditions, like the one shown here, a handcrafted controller is going to be a very big limiting factor. And additionally, you will need to identify a lot more affordances properties in order to craft a very complex controller to be able to drive in more complex situations. So this is not really scalable approach. However, affordance can be used as an auxiliary task during training or as part of the end-to-end learning to improve the performance. For instance, in this work from 2018, the authors took a pretty normal end-to-end system, and they added 2 more branches. One of them is going to predict the affordance values that I mentioned earlier, and the other one is going to predict some other values based on actions. And they found that when you do predict those auxiliary tasks, the training loss over time on the validation data set is going to decrease much more, as indicated by the blue curve here. Whereas without those tasks, the model is going to suffer in performance and plateau pretty quickly after training. So they can be beneficial as auxiliary tasks. and could be beneficial for downstream control predictions. Another way to use affordance is to use the affordance predictions to improve planning and make the planning safer. So in this 2023 work, well, this looks very complicated, but you may recognize from the previous lecture by Moshgan that this is a normal transformer encoder-decoder architecture, but we only need to focus on the output of the decoder, which includes some density map and some traffic rule predictions, the one that I mentioned before, the affordances. And in this work, they're basically using those predictions, and they have an end-to-end neural planner. So they're not directly doing the driving using exclusively the affordance predictions, but they're using the affordance predictions and to apply some safety constraint to refine whatever planned action the ego vehicle is trying to execute and make that safer. Basically not violate any traffic rules and not crash into any other vehicles, things like that. And the fourth way of improving the interpretability of end-to-end model is by explicitly doing the planning. Because previously, when the model is only outputting the action, you don't really know what the model is trying to do in the future. But with some explicit planning, you have some idea to visualize where the model is actually trying to go, where the vehicle is actually trying to go. And typically, this is followed by a traditional controller like a PID controller. So for planning, the task is really just to plan the ego vehicle's future trajectory. And there are a couple of ways to do that. The first one is called a waypoint prediction. And for instance, in this work from 2020, the way that they do explicit planning by waypoint prediction is by simply taking an image, going through an CNN, and outputting a heat map of where the vehicle should go. And obviously, the vehicle can have multiple modalities. So they output multiple heat maps of, corresponding to left turn, right turn, going straight, and so on. So, and then based on those heat map, they can extract the waypoint information, and you have a low-level controller like a PID controller to execute those waypoints. So this is a very simple way because the network can be entirely based on CNN and very simple in architecture designs. But the problem is, waypoint is very sparse, and you're going to be output a huge feature map that's mostly empty, right? And there's also no constraint that the waypoint that the output is going to be smooth and physically possible to drive. So another way to generate waypoints is by doing autoregression. For example, using a gated recurrent unit or typically gated recurrent unit. So in this work from 2021, for example, what they're doing is that they're taking the backbone features again from some feature extractor like CNN, and they are processing that feature with a GRU. So a GRU is similar to LSTM with some reset gate and update gate to update the internal memory. I'm not going to go too much detail into that. It's very similar in concept, but different in design. But this is also a recurrent network that's able to update or output one waypoint at a time to generate the entire future trajectory waypoint. So the second way to do explicit planning to generate trajectories for the ego vehicle is using a cost or affordance maps. So this is different from affordance values mentioned previously. So a representative work in this area is the neural motion planner NP from Raquel's group. So there are basically two steps if you want to use cost maps or affordance for planning. So the first one is you have a backbone network that takes your input. In this case, they're using LiDAR. And they're processing that to output a cost volume. In addition to that, they're also outputting some perception predictions, but those are auxiliary tests. And with the cost volume, what the cost volume represents is what's the cost of my eco-vehicle driving in certain locations. So in order to arrive at a final prediction or planned trajectory for the eco-vehicle, you would need to sample a wide range of trajectories to compute the cost for each trajectory based on your predicted cost volume, and then take the arc mean. So I want to be able to drive with the lowest cost possible. So a high cost situation would be, for example, you would run into another vehicle, you would run into some environmental obstacles and so on. So low cost would mean, drivable area that's aligning with the traffic rules and so on. So this type of trajectory planning method involves two steps. First of all, you need to sample trajectories, like I said, and then you take the arc mean based on the cost volume. So for trajectory sampling, there are different methods to do that. The first one, which is also employed by NMP, is they're using a mathematical formula of a curve. Typically, Bezier or a closed form curve would be appropriate, but you need to adjust the parameter of those curves based on your current eco velocity, so that the trajectory is actually drivable. You can also roll out a bicycle model as well, and you can sample a wide range of trajectories based on those generated curves. Another more realistic way of sampling trajectory is either using template-based, which means you generate a wide range of template trajectories based on your eco vehicle's motion model, or you can use retrieval-based, which means you collect the wide range of trajectories, either driven by the eco vehicle or driven by other vehicles, and then you retrieve from that large bank of trajectories some of the candidates based on your current eco vehicle speed, position, and so on. And those methods are employed by different works, different state-of-the works in recent years. So in the end, after we sample the trajectories, the training objective, because we want to learn a cost volume, but we don't really have a ground truth to do that, unlike other types of learning that I previously mentioned. So the training objective here is slightly different. We want the ground truth trajectory to have the lowest cost. So the objective here is to assign low cost to the correct trajectory. And this is done by using the max margin loss. And this is what it looks like. So this looks very complicated, but if you break it down, first of all, you have a first term that wants to maximize the difference between the ground truth and some randomly sampled trajectory, because when you randomly sample some trajectory, it's unlikely that it's going to correspond exactly to the ground truth. So in other words, it's a negative or incorrect trajectory for the prediction. So you want to maximize the difference in cost between those two. And in particular, when you minimize the loss for planning, you're minimizing the loss for the ground truth trajectory, which is the C hat super T, and maximize the cost for the incorrect trajectory. And in this NMP work in particular, they're also adding a term that measures the distance between the ground truth and the sampling trajectory. And this is here to encourage higher cost for farther away trajectories. So if you have a trajectory that's extremely different from the correct trajectory, you want that trajectory to have much higher cost than the other ones that may be close to the correct trajectory. And then another term is just for traffic violations. So it's a very simple cost, or a very simple loss function, maximizing the difference between ground truth and many randomly sampled trajectory. And in the end, this will give you a reasonable cost volume that can accurately predict the future trajectory for eco vehicle. Right. So this explicit planning was kind of popularized around 2019, and after that, pretty much all the end-to-end work that you're going to see are going to based on planning, or planning oriented, or they're trying to do explicit planning one way or the other. But to further improve the interpretability of modular or of end-to-end system, people started to develop what's called a modular end-to-end system. So in this case, the model is still end-to-end differentiable, and you go from sensory input directly to planning. But within the architecture, within the neural network, you're trying to kind of separate different components to the different tasks, so that when you finally fully train your neural network, you are able to output different interpretable tasks from the middle of the network. So, one simple way to achieve this modular end-to-end is to kind of handcraft some interpretable intermediate representations. And this is, sorry. So this type of approach is not initially, but it's proposed in MP3. This is another paper from Raquel's group from 2021, where they have a fully end-to-end system, but from diagram, you can see that you have very different, many different components that correspond to traditional self-driving stack, like perception, prediction, mapping, and so on. And of course, they're using a planning base, so they have trajectory sampling and some cost computation to finally arrive at the final trajectory. So the way that they made this architecture end-to-end differentiable is by enforcing some intermediate representations that kind of correspond to different tasks in the classical driving stack. For instance, they're trying to predict a drivable area in the form of a BV map. They're trying to predict intersections, reachable distance, reachable angle, occupancy by different objects. So this is very similar to the object detection task, where you need to identify different objects. And then temporal motion field, which represents the future motion of each object and their future occupancy. So this is similar to the prediction task in the traditional self-driving stack. But the key here is that all those output are going to be coming from the neural network, from a convolutional layer. So when these output are fed into the next layer, they're actually going to be differentiable end-to-end. Unlike our previous representation in the traditional self-driving stack, like bounding box or object tracks, those are highly filtered and highly condensed information. But in this kind of architecture, you can actually design as many information or intermediate representation as you like to preserve as much information as possible. So, right, I should mention that the one of the problem with this kind of end-to-end approach is that even though it's end-to-end, it's kind of similar to the drawback from a classical end-to-end system where you're losing a lot of information because, again, you're enforcing some representation, even though these representations can be trained end-to-end. So this doesn't really address the problem with that information loss. So recently, a new paradigm for modular end-to-end is what's called a query-based end-to-end system. So to understand a query-based end-to-end system, we first need to take a look at VIP3D, which is published in VPR 2023. So this is not a end-to-end self-driving architecture. It's a architecture designed for motion prediction and motion forecasting. But this architecture proposed a very interesting idea of using query as the connecting point between the input image features or LiDAR features and some output tasks. And it also shows that this kind of 3D query paradigm can be used in place of something like LSTM to connect temporal information and temporal data. So how this works is that you first want to initialize a set of queries. So these are entirely random. And so each query is basically a vector. The dimension of the vector is also arbitrarily defined. And these vectors are going to be trained along with the rest of the network so they can be optimized. The values can be assigned during the training. So you have some queries that's pretty fine and pre-initialized. So just like every other end-to-end system, you want to extract some image features or LiDAR features or for LiDAR modality. And the key here is that you're going to compute a cross-attention between your query feature and the image feature, where you use your query as the query in the cross-attention and the image feature as key and value. So in this case, the query is going to be updated by weighting the image feature based on the attention weight. So at each step, you do that cross-attention and your query is updated. And that query is updated so that it corresponds to one object, and it can contain all the information, including not only the position information, but also the appearance information from the image features that can be used to predict, that can be used to directly decode and predict trajectories. So not really inspired by this, but similar to this kind of query-based architecture for motion prediction, a very important work was published in CVPR 23. It's actually the best, I think the best student paper for CVPR 23, called Uni3D. They propose a new unified autonomous driving architecture framework based on this, entirely based on query to connect all the components together. So there are a lot of things to go through here, but first of all, you will have a what they call a trackformer, but it's basically similar to the VIP 3D I talked about before. You extract some image features and then initialize some track queries and then update those query features so that they are able to predict, or they're able to represent each object in the scene. But in addition to that, they're also having a what they call map former, which will represent static road elements like lanes or dividers. And this is exactly the same as a track former, but instead of representing the dynamic vehicles and dynamic objects, they're representing road elements and static sceneries. So based on all those information, they then combine those information into a what they call a motion former, but it's just a motion forecasting framework. So remember previously in VIP 3D, the motion forecasting is done directly from the, in this case would be the track formers features. But in Uni 3D, they're also incorporating the BV feature as well as the feature from the static map former. So this is what the map former, this is what the motion former look like, the architecture. It looks quite messy and complicated, but really it's just 4 components. So first of all, you would have some input, and the input is going to be the query from previous layer. And if you're at the first layer, the query is going to again be randomly initialized and optimized during the training process. And then you would have a lot of other information representing the position and the final goal position of the agent that you're interested in. And they're, fed into some positional encoding, which I believe Moshkan also talked about in the previous lecture. And then those are going to be your input to 3 different attention mechanisms. So the first attention mechanism is going to compute the attention between the motion query and the track queries. So recall that the blue here represents the dynamic object features. So you want to compute the interaction between the motion and the dynamic objects. And similarly, the motion query and the static map features. And finally, the motion query and the BV features, which directly comes from the input sensor. So in that case, so in this case, you would maintain, or you would be able to maintain and extract information directly from the input, unlike the previously mentioned intermediate representation, which are handcrafted and do not really benefit from this. So with all this information, the motion former is able to predict the future trajectories based on the updated features coming from all these components together. And then using the updated features, so in this case, the feature will represent really everything you kind of need to know about each agent in the scene, right? It represents its location, its past, represented the appearance because it's coming from the input sensor features, and it represents how it interacts with a static environment. So with all those information, they're able to train what they call an OC former, but it's just an occupancy prediction based on the BV feature. So they go from the BV feature and they attend to the agent feature, which include all those information, and then predict a occupancy map. So occupancy map would represent where in the scene it's going to be occupied in the future state. And that's going to facilitate the planning of the ego vehicle's trajectory. But the actual planning of the ego vehicle's trajectory is actually done all the way back in the motion former. Because if you pay attention here, where they have what's called an ego vehicle query. So they basically treat the ego vehicle as another agent on the road, and they initialize the ego vehicle's query all the way back from the start of the track former. So in the case, when you get to the motion former, you already have some predicted trajectory for the ego vehicle. And then you can actually just refine that trajectory based on, again, the input features from the sensor BV features, as well as the occupancy information that you know from the OC former to refine that planned trajectory all the way back from the motion former. So it's a quite complex architecture, but I think you can see that how this query and cross-attention architecture really elegantly connect all the different components and different tasks together into a single end-to-end system, and also how this design really avoids all the problems that I talked about with the classical architecture. Well, except maybe engineering complexity, because this architecture is insanely complex. But other than that, it's it's end-to-end, it's holistic. Every step and every module can benefit from input sensor information and all the other information extracted from the process. And the trend we can see nowadays is that this type of a query-based end-to-end modular end-to-end architecture is starting to become the future of end-to-end self-driving research. So a lot of the top conference papers on end-to-end self-driving, they all use this kind of query-based and modular design of end-to-end. Because there are a lot of papers on this topic, I'm not going to go into detail of every single one of them. They're all sort of variations of UniAD in one way or the other in some architectural design. But at the end of the day, they all use query and cross-attention to connect all the different components together in many different ways. Hello, everyone again. So this time, this is the end-to-end autonomous driving lecture part 2. So recall that from last time, I talked about the traditional autonomous driving stacks and a lot of problems involved with it, including the engineering complexity, and a lot of information are lost along the way, and errors can get propagated through the entire system. And finally, the entire optimization is not holistic. You're optimizing each component individually. And I introduced a end-to-end autonomous driving system where instead of having all those components, you just have a single neural network architecture that outputs action that you can use to drive the car. And last time I introduced some early end-to-end method and the evolution of a modern end-to-end method to improve the interpretability of the entire system. And so we introduced up to the modular end-to-end last time. So this time I'll finish up the architectural discussion with the VLM-powered end-to-end autonomous driving systems, and then briefly introduce some learning strategies, how to train an end-to-end system, as well as how to evaluate them, including open loop and closed loop evaluation. So for a VLM-powered end-to-end system, well, as the name suggests, we're basically replacing the end-to-end component with a large language model or vision language model, or sometimes a multimodal language model. So how do we actually use that to drive, right? Something like ChatGPT, how do we make it be able to drive our car? And what are some benefits? Well, in terms of benefits, recall the example that I showed last time when I was discussing uncertainty. So I showed this picture of a weird object on the road. And for a normal machine learning or a classical perception system, this situation can be very tricky because this object is not in the list of objects that we're trying to detect. Typically, we have a list of cars, pedestrians, and different commonly seen objects. But this is not one of them. This should be considered out of distribution data. However, if we ask, let's say ChatGPT or some large vision language model, what it is, and if I'm driving the car, what future actions I should take, then even though the large vision language model may not know what this object specifically is, as indicated here, this appears to be a large light-colored bag or a sack-like object, but the language model is able to output some plausible driving instructions that allows me, or in this case the system, to perform a safe action around this unknown object. So this is really the benefit of utilizing the diverse data that large language models are trained on. And like the example that's shown here, these methods are basically formulating the driving problem as a vision question answering task. So we're asking the model some question, and the model will provide us ideally the planned trajectory in the future. So like other categories of end-to-end systems, there are different ways to incorporate vision language model or large language model into end-to-end driving task. The first one is what I could call a directly driving with VLM. This is exemplified by this early work, from 2023, which is accepted by CVPR 24, called LM Drive. And this is a very simple implementation of this idea of driving using VLM, where they basically have normal navigation instructions input as tokens. I'm sure Moshe can introduce this concept, so you should be familiar with this. And to incorporate vision and camera images, they're using Q-former to transform multi-view camera images into a fixed size or fixed number of tokens, and then use the adapter to make it so that the large language model can understand it. And then the large language model will directly output, well, it says control signal, but it's actually waypoints for the ego vehicle to drive. And then you can use a low-level controller like PID controller to actually drive the vehicle. So this is a very simple implementation of VLM-powered end-to-end, but it has a few problems, and it doesn't really fully utilize the power of large language model. And in particular, it doesn't really use any of the reasoning capability that we have seen in recent language models like ChatGPT, especially the more recent O3 Mini, where it can do a chain of thought reasoning to answer questions more reliably. So it doesn't have that. And because of that, this model really doesn't have any of the interpretability that exists in previous modular-based end-to-end systems. So in more recent work by Waymo, they're trying to improve this type of architecture by instead of letting the large language model output directly driving actions for future planned waypoints, it will instruct the model to think step by step and to have a chain of thought reasoning so that the driving planned trajectory is more robust. And in this case of Emma, they're trying to first let the model identify critical objects. So in this case, you have a cyclist in a vehicle, and then the model will be instructed to describe the behavior of those critical objects. And then based on all that information, it will make a meta driving decision and then have some planned trajectory that the model, the vehicle can actually follow. And just like what we see in normal large language model in complex reasoning tasks like math problems or programming problems, instructing the model to think step by step can actually improve the performance by quite a lot, as shown here in their ablation study, where they gradually add different levels of chain of thought and evaluate the end-to-end planning results. And as you can see, when you add critical objects, meta decision, and behavior description, the planning performance can improve by quite a large percentage. And this really demonstrates the large language model's ability to reason and to actually drive the vehicle, or the potential rather. And in addition to just doing the chain of thought reasoning and output the future trajectory, this model, Emma, actually is trained on multiple tasks at once. So you can actually visualize, for example, object detection results directly from the large language model, because one of the prompts is instructing it to output coordinates for the objects, as well as the lane location. And this, it first improves the results based on their results, or improve the planning based on their results, but also makes the model more interpretable, because these are understandable representation that humans can understand. However, if you are letting the large language model directly outputting some numerical values, some coordinates, you run into the problem of how accurate are those numbers, because we know that from experience, large language models aren't exactly it doesn't excel at those tasks, numerical tasks. And also, how do we guarantee the future trajectory waypoints are actually realistic to drive based on your current vehicle speed? It's a whole, again, it's a black box. You don't really have any control over those. So in one of the recent work, this is actually published 5 days ago, called Orion, which obviously stands for Holistic End-to-End Autonomous Driving Framework by Vision Language Instructed Action Generation. They try to alleviate that problem of letting the large language model directly generate the numerical values by using a generative planner. So let me just go through this model or this architecture real quick. So first, they have a normal vision encoder, goes into a Q-former, which translates the tokens into something the large language model can understand. And this is very similar to the LM drive that I introduced before, where you have some adapter that transforms the image into something the large language model can understand. And then just like Emma, it also outputs multiple tasks and a chain of thought reasoning for their action. But instead of outputting directly the waypoints for the ego vehicle to take in the future, it outputs what's called a planning token. So the planning token is basically a special feature vector that will be fed into a generative planner. So generative planner is a VAE-based generative model, which takes the planning token, maps it into a feature space, and then based on the feature, it will start generating future waypoints using GRU. This is similar to what we discussed before with the modular or planning-based end-to-end system where you generate future trajectories waypoint by waypoint using an autoregressive model. So in this case, the way that they avoid the problem with generating numerical values from large language model is by having some generative specific generative model that's designed to generate realistic trajectories for the ego vehicle to take. And as we can see from recent publications,
I guess just quick question at this point. When you pass the tokens, I mean, you still have the issue that, well, maybe the trajectories are not accurately representing the spatial positions of the objects, right? Or respecting.
Yeah, exactly. Yeah. So this model runs into the problem of whatever you have, whatever information that you're reasoning about here may not reflect the final trajectory generated by the generative model.
Right.
Yeah. So that's kind of a limitation of this kind of approach, because they kind of disentangled the trajectory from all the reasoning and all the scene description.
Quick question. So, like, would you run the generative trajectory with multiple like the tokens and like generate multiple by having like multiple tokens and have that as like the initial like seed for the VAE?
The seed for the VAE,
or I guess like the Z value.
from my understanding, yes. Depending on how many trajectories or future possible trajectories you want to generate.
Okay, cool.
Yeah,
that makes sense. Thanks.
Hi, Nick. I also have a question.
Yeah.
So do you know if they're considering time? Because I see not Q former, but QT former for their project. Yeah. So T stands for time, yeah? Okay.
Yeah,
do you know
temporal,
how many seconds? Yeah. Okay. How many frames they are considering? It's just
I'm
details.
not sure.
Yeah, that's okay.
Yeah.
Thank you very much.
Yeah, they modified the Q former to include multiple frames and temporal data. Yeah.
Cool, thanks.
Cool. So yeah, we have seen a lot of work recently in top conferences, as well as by industry leaders like NVIDIA or Waymo. They all developed their own version of driving directly with VLM and different variations of that. And of course, if you're interested in Waymo's EMMA, because it's not open source, there's an open source version or recreation of that in WACB 25, and the source code is also available. So the main problem with directly driving with VLM is, of course, the runtime efficiency. Large language models can be very large and very expensive to run in real time. And a more concerning problem is, how do you verify the safety of this kind of system? I would argue it's even more difficult than the traditional modular end-to-end system, just because the large language model can hallucinate and it can make very confident mistakes, as we have seen in the past from all the other large language model that's available to us. So however, for runtime efficiency, we can do something about that, which leads us to the next paradigm. And yeah, so another way, the next way to incorporate VLM into our end-to-end system is what I would call VLM assisted planning. And some people will call it the fast-slow dual system, which is inspired by human reasoning and human thinking, where we have a fast reaction or fast thinking in your head, and then we have another system for slow reasoning. And this kind of inspires the creation of a dual system, fast-slow dual system. So this idea is first implemented in Drive VLM all the way back in 2024, where they have a normal large language model, vision language model, to do all the reasoning, scene description, and high-level planning. But in addition to that, they're employing a traditional classical autonomous driving stack. So you have the perception, prediction, and trajectory planning module. But to incorporate the knowledge and the results from VLM, they are incorporating the tokens generated from the VLM into their trajectory planning stage to basically refine the trajectory. So the VLM will generate a rough trajectory, what they call a low frequency trajectory. And that serves as an initial point, an initial proposal for the future trajectory. And the trajectory planner will then take that as input to refine that and generate a high frequency trajectory such that the whatever controller you're using can actually follow. So, well, technically this is not end-to-end, but in a more recent work called Senna, they have a very similar system, but instead of using a traditional self-driving stack, they're using an end-to-end system. And this end-to-end system is exactly the same as the ones I described in the last lecture, the query-based modular end-to-end system, where all the modules are connected by feature queries. And because of that, the fusion between the end-to-end planning results and the vision language model results can be very easy. It's just another cross attention where the planning query needs to pay attention to the feature vector coming from the large language model. And again, this is utilizing the VLM and making meta decisions for the planning to plan the final trajectory.
Quick question.
Yep.
Like before, you showed that like it took like 5 seconds to like reason about like some sort of input. What like if like the data is no longer relevant, like how would we filter that out, or is that like part of training for the attention to like notice that it's no longer relevant?
Oh, that's actually a good question. Well, everything will have a timestamp in the end, and so I would assume that the system will be, during training, will be forced to learn that kind of information. But I do not really have a good answer to that.
Okay.
Yeah.
Thank you.
A lot of the work are quite recent, and a lot of details I don't really know. So another system architecture that's quite different from the ones proposed in the previous two are what's called a LEAP AD. So they also have a dual system for fast and slow reasoning, but it's quite different because they're employing what's called a memory bank. And the way this functions is that the slow system, in the previous two examples, the slow system will basically run continuously. But in here, the slow system will be triggered once the fast system makes a mistake. And upon making a mistake, the slow system will be triggered, and it will start reasoning about what's causing the mistake, given past few frames, and it will reason which frame I should do something different and why I should do something different, and what's the final decision for avoiding that mistake. So it's kind of a reflecting on your own mistake. And after this reasoning, the fast system at runtime will start doing a retrieval task from the memory bank. So the memory bank is basically all the past experience, all the past mistakes that the fast system has made. And depending on the scene, the appearance of the scene based on the feature similarity, it will do a retrieval task from the memory bank to prompt the fast system. So the fast system here is actually another language model, but it's a very small language model. So it's much smaller than the analytical and slow language model. So it can run much faster than the slow system. And the hope is by retrieving all the previous experience, the fast system can make better decisions. So this is another way to design this kind of system by having a memory bank with all the previous experiences. So yeah, again, this type of usage of visual language models have seen some publications in top conferences and more recently on arXiv. And even in industry, Li Auto, which is one of the leading consumer vehicle manufacturer, incorporate this kind of system, fast-slow reasoning system, already into their product. So here's an example of the auto vehicle driving on the road. And on the right, you can see there's a visual language model triggered periodically to describe the scene and make meta decisions. And then you have an end-to-end model that's being run in real time, planning out the future trajectory. And of course, you can see there's an attention map that we described last time. So yeah, in summary, we talked about how to make end-to-end autonomous driving system more interpretable with uncertainty, but that's not really realistic. And typically the uncertainty estimation can be very inaccurate. We talked about saliency and attention maps, but they offer us limited information, some information, but quite limited information. And recent work, we have seen some paper utilizing affordance learning to make the interpretability more explicit by predicting affordance values and having a handcrafted controller, which have evolved into planning-oriented end-to-end, where the model will output directly the future trajectory, which can handle more complex situations. And to make that even more interpretable, we have seen modular end-to-end, where the entire system is divided into sub-modules, but they're fully differentiable. And what's connecting the different modules can be some handcrafted intermediate representation, or it can be query-based, like we've seen last time, utilized by many work. And the recent VLM-powered end-to-end planning, which is built upon all the recent advancements we have seen so far. So yeah, in summary, the future of end-to-end autonomous driving is really the query-based for traditional architectures and the VLM for end-to-end planning, and how to make VLM more interpretable and how to make VLM more efficient. So that's it for the architectural part of end-to-end driving. And next, I will briefly talk about the learning strategies and evaluation methods. So before we talk about the learning strategies, we need to go back to the really simple end-to-end method, which is few layers of convolution networks by NVIDIA. So how do we train this type of a neural network to drive? Well, we can do that by formulating this as a behavior cloning problem. So the behavior cloning strategy of training end-to-end system. Well, in this strategy, we first need to have some kind of reference policy, typically a human driver, which I labeled pi sub beta. And using that pi sub beta human let's say a human driver, we can collect some data set in the actual environment with the state and action pair at each timestamp. So our goal for learning another machine learning end-to-end driving policy is basically by minimizing the loss, or by minimizing the difference between the action coming from our end-to-end model and the action from the reference policy. In other words, human drive. So this is basically a supervised learning problem, and it's quite simple. You just take the ground truth and you take your model's predicted output and compute the difference. For steering angle, for example, it's just the difference in steering angle. And for trajectory planning, you're just computing the distance between the waypoints. However, this strategy has two major challenges. So the first is what we call a covariate shift. So let's suppose you have some policy trained on a ground truth. Trained on some human demonstration, and then it starts to make a mistake at some timestamp t. So when you roll out this policy, it may make multiple different mistakes, and it may diverge from the human policy at different times. So what will happen next is that it can lead the vehicle into a state that it has rarely seen during the training, which means the vehicle doesn't really have any data to recover from that situation. And the mistake then compounds over time. And in fact, it's proven that if you have some small probability of making a mistake at some time, the total cost, or the total divergence from your reference policy is going to grow quadratically over time. And that's because you don't really have any data to recover. And the vehicle will just spiral out of control. So how do we solve this problem? There are a couple of strategies that people have developed. The easiest one is just to incorporate some recovered data. And this is actually noted all the way back in the 1980s. The last time I talked about the Alvin, and in their paper, they noted that the network must not solely be showing examples of accurate driving, but also how to recover once the mistake has been made. But obviously, if you're talking about on-road driving, this can be very dangerous, and some mistakes you just don't make on public roads. So another technique people have utilized is data augmentation or simulation. So in that NVIDIA car, what they're actually doing to train their neural network is by randomly shifting and rotating the input image and then adjusting the steering angle based on how the image is shifted and rotated. So given some input image, you can compute a very simple transformation to kind of shift your image location. And in addition to that, they are also employing a 3-camera setup. So it's easier to kind of interpolate between the different viewpoints. In another work, they found that just incorporating data augmentation and simulation might not be enough. And instead, you also need to inject some noise. This is only possible really in simulation. So when they're collecting their data in the simulation, randomly at some point, they will start injecting noise, which is indicated by the red curve. And the human driver that's driving the vehicle is going to try to correct that. However, the vehicle is still going to have some deviation from the normal correction action. And then you can use the human driver's corrective action as the label to correct the vehicle onto the correct trajectory. So this is kind of like incorporating recovered data, but it's a more efficient way of doing that in the simulator. And the final way is to just have a large amount of data, because the main problem with covariate shift is some edge cases and some situations you don't cover in your data set, causing the model not knowing what to do in certain situations. So in another recent work by Wave, so they are an autonomous driving company that has a lot of money. So they just drive around the city of Cambridge and collected a lot of data. And they found that this can alleviate the covariate shift problem. Of course, if you're testing your vehicle under a different domain, this might not work, but this is another technique that can be used in conjunction with the other ones.
Quick question. With the data augmentation, so like we have the visual aspect of like shifting left or right, but like it won't like fully, it might not like fully like capture like the traction. Like for example, if you shift to right onto grass, and like the surface would be different. So like do they also augment like bumpiness?
No, not really. No. They're just augmenting such that if you follow the augmented steering angle, the vehicle will be back to the center of the lane in like 3 to 5 seconds. I forgot the exact number, but it's a handcrafted formula to calculate the adjusted steering angle. So there's no fancy formula for that. But this is also a quite simple and early method that only does lane following. So yeah, those factors were not considered.
Okay, that makes sense. Thank you.
Yeah. So that is covariate shift. The second challenge is called causal confusion, which means the model during the course of training might learn some spurious correlation between the previous state or action and the current output signal. So for example, recall this conditional imitation learning architecture end-to-end system that we discussed in the previous lecture. The input to the system, in addition to the current image, will also have a measurement from the previous state. And the measurement is obviously, reflective of your previous action. And there might be a very strong correlation between your current action that you're trying to predict and the previous action, which resulted in a certain measurement of the ego vehicle states. And this kind of correlation can manifest in two aspects. The first one is a steering angle correlation. And this is noted by Yann LeCun in 2005 when he was developing his small robot for obstacle avoidance. And he noted that a steering angle is very smooth in time. And as a result, the current rate of turning is an excellent predictor for the next desired steering angle, which totally makes sense. So if you're training a system and input all the previous steering angle and predict the next steering angle, the model might simply just ignore your current state from your camera or other sensors and establish the spirit correlation. Another correlation that's commonly seen in autonomous driving is speed and braking. So this is noted in a more recent paper. They noticed that when there's a very strong correlation between the vehicle's previous state, for example, stationary, and the next state, which is, do you want to step on the gas pedal or not? So, for example, let's say the vehicle is approaching a red light. The correct reasoning for the end-to-end model to do is do the braking because it sees a red light. But instead, what the model might establish a correlation between the previous speed, which because you're seeing a red light at some point, so the vehicle might be slowing down, and the predicted speed. So it's braking not because of the red light, but because of the current speed is slow, and maybe your speed is going even slower. And they thought this problem an inertia problem, but it also is reflective of causal confusion. But can we simply avoid it by removing the feedback input? So using the previous architecture as an example, can we just not input in the measurement, but just use the image? Well, not if the model uses sequential input. And this is because if we model this whole process as a MDP, and then removing the input measurement is simply removing this green connection between the previous action to the current action. But we have to notice that the current state that the model is going to observe is actually influenced by the previous action. So there's an implicit connection between your previous action and the current action. And if your model is using a sequential input, which means that it's using multiple previous states, then this information might be leaked through the state update, and the model can still establish the spurious correlation. So what do we do? What solution we have? Well, the simple solution is just don't use multiple frames. Just don't use sequential input. And this is noticed by Yang and Kuhn, who at the time believed it's impossible to train or do behavior cloning for this kind of problem by using multiple frames because of the causal confusion. However, this is not a very ideal solution because we know that temporal information can give a lot of context and can be very beneficial for autonomous driving. And this is also not how human thinks and drives as well. So many different other methods have been developed. The first category is regularization. So you can append some auxiliary tasks to your network. In the case of this paper, they proposed to append a simple speed prediction task to the image perception module. And you may say how that's going to help the causal confusion. What their reasoning is that because there's a correlation between the measured speed and the final action, then if we predict the speed directly from the perception module, then there might be some features containing information about the speed in the image features, such that the conditional module that's going to output the action is not going to rely entirely on the measured speed, but it can use the predicted speed as well. But that's a very heuristic method. If it works, it works, and they showed that it improved the performance. So another regularization is similar to what we typically do in neural network to avoid overfitting is called dropout. So in this method, where the input to their network consists of a lot of different things, but most importantly, it includes the past agent's poses. So this will cause the feedback problem. So how they avoid that is by randomly dropping out this input such that the model will not rely too much on it. The generalize better to situations. So another family of more involved method is it involves some information theoretical analysis. But I won't get into too much detail, but the main idea is, let's say you have a model that's going to output an action for the current timestamp. And there's a correlation between the previous timestamp or previous action and the current action, which means that somewhere inside your neural network features, there contain some information about the previous action. And in those information theoretical methods, they're trying to make it so that the feature extractor will remove those information about the previous action, but retain all the necessary information to accurately deduce the current action. So to give an example, this can be done via adversarial training. So the E network, the encoder, is going to take in multiple observations. This can be an image sequence or LiDAR sequence, and then output a feature vector. And the feature vector will then be used by the F network to determine the current action, current timestamp action. However, in this adversarial training method, coming from the same feature vector, the feature vector will also be fed into a D network, a discriminator sort of network that will try to predict the previous action. Now, how this is trained is why this method works. So the D network is trained, it's optimized to correctly predict the previous action. In other words, it's trying to, deduce the previous action from the feature vector extracted from the encoder. However, because we don't want any information about the previous action inside the feature vector, the encoder for the images are optimized such that the D network cannot really predict accurately the previous action. And this is adversarial training. So if you know about GAN, this is similar to that. And it's just a game of one is trying to predict this value and the other encoder is trying to prevent it from predicting this value. And the only way to prevent it from accurately predicting the previous action is just that the encoder removes all the information about the previous action during the encoding process. And because we're also training the F network to accurately predict the current action, then what's left in the encoder's feature are going to be informative of the current action. So some other regularization term can also be
just, I guess, maybe just question, comment, or I mean, yeah, that all makes a lot of sense. But I mean, presumably in the majority of cases, the same state that is causing current action was causing also the previous action. So I guess this is just going after the sort of minority of cases where the action is changing, right? So
yeah,
question how effective that is, right?
Yeah, that's indeed the minority cases. I think typically when they train, they also do balance sampling, so they don't sample all those easy cases.
Yeah,
where the vehicle is driving straight. Yeah.
Yeah. So, but if you train it basically just to focus on the cases where you have to, learn to make the decision, change this decision, then I think that would address it. Yeah.
Yeah.
Another quick question. Is there anything special about like the very last action? Like, would we want to also have a discriminator for like past actions before T-1? So like T-2 and.
That is true. Well, that's actually a very good point.
Because if we can get back like T-2, T-3, we can probably estimate T-1.
Yeah, I guess the problem with T-1 is the connection is there's very few connection between T-1 and the current action. So I would say, if you go from T-2 to the current action, that may be a more difficult task, but that's just my assumption.
Okay.
But I could see that it's reasonable to add more discriminator for past actions as well. Yeah. Right. So so another information theoretical method that's even more involves having a closed form regularization that minimizes the conditional dependence between the previous action and current action. And in this paper, they're using Hilbert-Schmidt conditional independence criteria. And if you're interested, you can check out that paper. And like Christoph mentioned, another way, if you simply want to train your model to perform better at those situations where the actions are changing, then you can just do some importance weighting. which is exactly what this method is doing. So this method proposes a very clever way of identifying the situations where the actions are changing, but if you have some model that established a spurious correlation, then the model will make a mistake. And during training, they will assign a higher weight to those situations where the actions are changing and the model will make a mistake. Yeah, and that turns out to work quite well. And the final type of solution to this problem is incorporating single frame predictions. So because we know single frame doesn't really have this problem of cultural confusion, so if we can incorporate that single frame prediction into our multi-frame model, then presumably that will make the model better. And in this work, for example, they have another branch to take in key input, which are basically single frame input. And they have a normal end-to-end model to predict the future action, which they call the priming variable, because that variable is going to be fed into your multi-frame architecture end-to-end system to basically make the system aware of your single frame prediction. And the two branches are trained on the same ground truth. So in this case, what they are arguing is that the model will take the easier branch, which is the single frame input, which can be indicative of the future action in most of the cases. But when the raw input, which is the multi-frame input, can be beneficial, the model can also utilize information from that as well. So they have some analysis of this using a very simplified model and a lot of assumptions. Another very similar variation of this, they also have a two-branch system where you have a branch for the single frame input, and you incorporate multi-frame features in the middle. And what's interesting about this work is that the multi-frame branch is not trained to predict the action, but is trained to predict the residual action from the single frame input. And they show that this is a valid approximation to the upper bound of the mutual information between the current action and the previous action. Right. So that basically concludes the behavior cloning and the two challenges involved with behavior cloning, as well as a lot of the heuristics and solutions designed to combat those problems. Even so, those problems still exist if you're just using behavior cloning. And that really mainly stems from the feedback problem and the fact that the model is trained in a single run and you don't really have any means of gathering more data in the distribution where the model can make mistakes.
So wait a second, the guy, I'm also thinking that if you had sort of more semantic layer, just like, for example, the VLM, that perhaps was basically, has access to the knowledge of what actually is a good action in a given state, right? So it basically it's not trained in terms of behavior cloning, right?
Yeah.
Then you could use that also as an input into your underlying model, right? As a of course that wouldn't be just purely cloning, but you could imagine sort of having similar, I suppose, like what you have right now on this slide, kind of a dual system, right?
Right.
Just basically a remark here.
Yeah. Okay. Yeah, actually, most of the recent works are just trained using basic behavior cloning methods for several reasons. Well, it's kind of simple, and also a lot of them are doing evaluation on open loop benchmarks, which doesn't really have this feedback problem because the environment won't be interactable. But yeah, the behavior cloning is still quite widely used in research. But to kind of fundamentally address the challenges or the limitations of behavior cloning, another better method is called online imitation learning. I should note that behavior cloning is actually considered a type of imitation learning. It's a very basic form of imitation learning. So for online imitation learning, you would iteratively roll out and update a policy by kind of interacting with the environment and then querying some expert policy. So recall this diagram from behavior cloning. What the imitation learning is doing is adding another branch where after deployment, you would also collect data from the learned policy into your data buffer and label them and then update the policy to deploy in the environment again. So several representative and notable methods in this category. The first one is MAO. So they start with the expert policy and then gradually roll out and mix in the learned policy. So this is their algorithm. It looks complicated, but really it involves 3 steps. First of all, you would execute some policy that's initialized to the expert policy. So in the very first iteration, you let the expert drive the vehicle. So the blue line here is the expert trajectory, and collect the data. And you train another policy using behavior cloning. And the policy is going to not do very well in the divergent, all that. But the important step is this red, what I highlighted as red, where you mix the expert policy and your learned policy in the next iteration and roll out in the environment. So in this case, you would have a mixture of expert policy and your learned policy, which is going to make a lot of mistakes, and expert policy and learned policy. And the expert is then going to label all the mistakes, and the training will then, you will be trained on the updated data set and updated labels from the expert. And they show that on average case, this actually achieves better than quadratic error accumulation. But in the worst case, it's still quadratic. And the main problem is that the data from the previous iteration is actually thrown away. So the model is entirely possible for the model to make one mistake in one iteration, correct it in the next iteration, and then make the same mistake again in the future iteration. And there's no guarantee to prevent that from happening. And this kind of inspired the development of Dagger, which is also an iterative algorithm. It iteratively rolled out the learned policy, query the expert for ground truth actions. But the most important part is that they aggregate the data set. So in each iteration, you roll out the policy and then let the expert label all the actions and then combine everything into a big data set. And the next iteration, the policy is going to be trained on the aggregated data set. And in this paper by Ross, they showed that this algorithm can achieve the theoretical optimum of a linear error or linear cost over time. Mistake will not compound if you train the system long enough, at least theoretically. But this has a big problem. First of all, you're going to aggregate the data set, so the data set is getting larger and larger. And more importantly, every step you're going to need to query the expert and let the expert label every action. And this can be very difficult, especially for a human driver. And even if in simulators, if you're just watching a video of the car making mistakes and try to correct it without any feedback from the vehicle, the corrective movement can be quite inaccurate. Just thinking about driving a car, but you're not actually driving the car. You're just watching a video of a car driving itself. So we Yeah.
Okay, sorry. Yeah, quick question. Like when actually evaluating the policy pi on like a state, is this like in a simulator usually? Like, or would like the training actually happen in an actual car?
You'll just let the model drive, and if it makes a mistake, you terminate your data collection.
Okay, like the training, like the data collection would happen in an actual car.
I'm sorry you cut off in the end.
Oh, like the data collection would happen in an actual car.
So this algorithm doesn't really specify. So you can perform your entire experiment in the simulator. Then the data collection and your data is going to be entirely simulated. But this is another problem, is that you, because you need to roll out the policy, it can be quite dangerous if you want to do it in real world. Typically, it's in the simulator if you want to do that.
Okay. Yeah. Thanks.
Yeah. So yeah, because of the policy or the expert querying problem, we kind of need to improve the efficiency of the reference policy. And there are a couple of ways to do that. First of all, you can, for simple driving conditions, like in this paper where they just drive around a dirt road, you can use an algorithmic expert where you construct some handcrafted algorithm based on some sensor input, and then have another deep neural network try to kind of distill that policy by using the algorithm. And in this situation, you can actually drive in the real world to collect data and label the data. Another more popular and recent way to, so yeah, for a privileged agent, basically means that the agent doesn't, not only has access to your input information, but also has access to some privileged information, such as the ground truth. And typically this, of course, can be done in the simulator where you have access to the ground truth. So in this case, you can just use normal imitation learning or behavioral cloning to train a privileged agent. But the agent input is going to be ground truth instead of some sensory motor input, like camera images. And then you then use that privileged agent as the expert reference policy to distill another agent that takes camera images or other sensors input as input. And this is also done in another work, but in this case, their privileged agent is trained using reinforcement learning in the simulator as well. And another improvement for Dagger is to improve the data efficiency, because you're aggregating a lot of data and you're trying to query the expert a lot of data, and that all of that data might not be necessary. So one of the first way to do that is called Safe Dagger. So the algorithm for Safe Dagger looks quite complicated, but the most important step is that after collecting the data, they will use a safe classifier to select subset of the data that they have collected to aggregate to the entire data set instead of aggregating all the data. So in other words, here's a rough visualization of that. So instead of aggregating the part where the vehicle is kind of driving correctly, you only aggregate when the vehicle makes a lot of bad mistakes. And in that case, the expert only needs to label those situations. So the ARB works in a similar way, and the ARB stands for data aggregation using replay buffer, where they incorporate a critical state identification and a replay buffer to kind of filter the data set to make it manageable. And in this case, they're sampling what they call critical states from the data that has been collected by the learned policy. And this can be identified based on your task. For example, we know that driving straight is not as interesting as making left or right turn. So that can be a identification factor. And last time we talked about epistemic uncertainty, and in that paper they also suggested that epistemic uncertainty can be used to identify those critical cases, or you can simply take data where you have a very large loss based on your compared to your ground truth and select those data. So this is basically subsampling whatever data you have collected to make the expert job easier. And then they have a fixed size buffer where at each stage they're dropping some data that's similar to the initial expert driving example. So this is under the assumption that the vehicle is not likely to make those easy mistakes as the training goes on. So Smile and Dagger, they kind of works, but they have another problem that has been identified. So let's suppose we have this situation where the vehicle is driving on a 2-lane road where the left lane is turning left and the right lane is going straight. So for the expert policy, you would want to go straight. Maybe the vehicle needs to go straight. But then the vehicle makes a mistake. However, before making the mistake and after making the mistake, the vehicle is driving perfectly according to what the expert would drive. But it's making a mistake such that the trajectory for the vehicle is diverging by quite a lot. And the vehicle, if it makes a left turn, it can end up in a very bad situation, maybe not in its final destination. So in other words, the mistake that it's making here is a very high cost mistake. And for Dagger, where you want to label every mistake action and average the cost, this mistake or this entire driving situation would not have a very high cost because you're just making a very small mistake here and then driving perfectly elsewhere. But this is not really reflective of what we want from the model. So to reflect that, another algorithm called Aggravate, similar to Dagger, but instead of querying the expert for correct actions, they're trying to query the expert for a value for the action, what they call a cost to go, which kind of reflects how bad a mistake would be if it happens at in different states. So this compared to Dagger is even more difficult to actually implement in real life, because how do you even ask a human to label this kind of things, right? So this is really, I want to discuss this as a theoretical situation. But we do have a way for the model to actually learn the value instead of querying the value from an expert. And that's falls into the category of inverse optimal control, or also called inverse reinforcement learning. So the setup for this learning algorithm is quite similar to behavior cloning, where you have some reference policy, you collect the data using the reference policy, but instead of matching the output action from the model to your reference policy action, you're trying to learn a cost or a reward function based on your action state pair. And then in deployment, you can just choose the action with the lowest cost and highest reward. So this avoids the problem of acquiring the value or reward from the human, but instead of learning that directly from human demonstration. So this is quite tricky to actually implement in autonomous driving, but there are two notable methods of doing that. The first one, I guess, could loosely fall into this category, is called generative adversarial imitation learning. So what this method does is that given some sensor input and end-to-end planner, which will generate some trajectories, you would have another discriminator that takes in generated trajectory as well as a real trajectory and try to determine which one is real and which one is generated. And it's trained adversarially so that the discriminator is trying to optimize to generate correct predictions. And the end-to-end planner is trying to basically fool the discriminator and make the discriminators make mistake. In other words, try to generate correct and realistic looking trajectories. So in this case, in the reward or the actual cost function is implicit through the adversarial training process. And there are different variations of GAL, like InfoGAL, MixGAL. I put the reference down below, with different improvements over the original design. So another method to implement inverse optimal control is what I actually talked about last time, the cost-based explicit planning. So recall from last time when I talked about a neural motion planner where the model is going to output a cost volume, and then you're sampling a lot of trajectories and picking the one with the lowest cost. That's basically, the problem formulation that I presented in the previous slides. And in the last time, I also talked about how you would train such a system to assign lower cost to the correct trajectory and assign higher cost to the incorrect trajectory using a max margin objective. So I won't talk about that again this time. And the final way of learning or training an end-to-end system is reinforcement learning, of course. I'm kind of out of time, so I won't talk about that in more detail, but compared to imitation learning and inverse imitation learning, the key point of reinforcement learning is you're interacting with the environment and you're receiving feedback, either rewards or penalties from the environment. And of course, there are many different methods. I'm sure there's dedicated course for reinforcement learning to talk about all those methods. But in the context of autonomous driving, the difficulty for reinforcement learning is that it requires a interactable environment, which typically cannot transfer to a real world driving condition. However, recently we have seen a lot of advancements in neural rendering, like 3DGS and generative models. So we can actually generate quite realistic looking simulations to do that. And in a very recent work published last month, they're doing that with reinforcement learning. They're incorporating a 3DGS virtual environment into the training process. So first, in the stage where they train the planner, they're using a basic behavior cloning imitation learning. But then they have another stage where they further optimize the autonomous driving policy by rolling out the policy into a virtual environment generated from the 3DGS and using a PPO to update the autonomous driving policy. And it's mixed with human driving demonstrations as well. So yeah, and finally, I'll talk about how you would evaluate a end-to-end driving system. So there are two types of evaluations. The first one is called open loop evaluation, where you're testing your model on a pre-recorded, typically real world data. A notable example of the data set for this purpose is new plan, which is based on new scenes. And the metric for this is quite simple. You're just computing the average displacement error between the waypoints and the final displacement error between the final location and the miss rate. So the miss rate is the rate where your planned trajectory or planned waypoint is much further away above some certain threshold compared to the ground truth. This evaluation is employed by a lot of methods, but because you're testing on the pre-recorded real-world data and there's no interaction between your vehicle and the world and other agents, the errors will not compound because there's no feedback. So you can't really test your model for those mistakes. Which leads us to the closed-loop evaluation, where in this case, you're testing in a simulated environment, and your action from your model can actually influence the future states of the environment. Typically, a very popular simulator is called Carla. And the metrics are a little bit different because the environment is dynamic. So typically, they would set up an environment and an objective for a starting point and endpoint. And the model would be tested to drive the entire environment and have some driving score, route completion percentage, and some infraction penalties. So in the Carla benchmark, for example, the driving score is the product of route completion percentage and the infraction penalty to kind of adjust the driving of the model. And infraction penalty can mean collisions or traffic violations for some off-road driving. And obviously, because it's a simulator rendered in computer-generated graphics, there's a domain gap from simulation to real. So it's kind of difficult to evaluate the real-world performance of those models just in the simulator. However, like I said, with the recent advances like 3D and more importantly, world models, you can actually do quite realistic closed-loop evaluations using those technologies. A very notable example of world model is by Wave called Gaia-1. So the model, the world model, basically given some past video input, you're trying to predict the future. And this is done auto-regressively using a transformer architecture. So you take all the input, and in this case, they're also actually using text prompt world model. So you tokenize everything, feed those input into a transformer, auto-regressive transformer, and then it's going to predict a bunch of other tokens that can be interpreted as future frames. So this can be quite useful because given the same initial frame, the model can actually predict very diverse outcomes into the future, which means you can test the vehicle in very diverse environment that in this kind of world model simulations. And not only the future, but it can also transform or given some traffic situation, it can generate similar situation, but with different building, different cars and different weather conditions and so on. So yeah, that concludes the lecture on end-to-end autonomous driving.